4A, correlation. So now we're going to start talking about what we call bivariate data. Bivariate data is data that deals with two variables at the same time, essentially x and y, an input and an output. When we're dealing with bivariate data, we tend to use ordered pairs. Ordered pairs, you've seen them before when you plot points on a graph. X and Y, an ordered pair. Maybe that's someone's height and someone's weight. Tied together, they relate to one another. Right? Someone's age and shoe size. They're related together. It's not a separate piece of information. They're just two different variables that relate to one particular subject. We tend to refer to this first variable, x, as the independent variable, and the second variable, y, as the dependent variable. Meaning that x is what everything's based on, and y depends on x. Now, correlation is actually studying how much does the dependent variable really depend on the independent variable. And that's what we're going to be checking to see as we deal with this. So first thing we're going to do with this is we're going to put a set of data points up here, some bivariate data, and then we're going to create a scatter plot. So let's get some data up here. So I'm going to do, let's do driving time. So I'm going to say time in minutes and distance traveled in miles. So I'm going to ask some people, how long did you drive for and how much distance did you cover? So the first person drove for 51 minutes, and in that time they drove 56 miles. Second person drove for 29 minutes, and in that time they drove 14 miles. The third person drove for 64 minutes, and in that time they drove 24 miles. Next person, 68 minutes, and in that time they drove 48 miles. Another person drove for 94 minutes, and in that time they drove 86 miles, and then somebody else drove for 33 minutes, covering 25 miles, and our final person drove for 89 minutes, and in that time covered 66 miles. So now we have our bivariate data. We have the time that they traveled and the distance that they traveled in that time period. In general, and in this course, always, your independent variable is going to be that first column, and your dependent variable is going to be the second column. It is rare that people swap those, but I can guarantee you in this class that that will never happen. So you're always going to have your x variable followed by your y variable. Now, I want to create a scatter plot because this is great. I see this, but it's just a bunch of numbers in there. And we know that graphs always make things easier for us to obviously visualize, but many times make it easier for us to understand. So as I said, I'm going to put the time on the x-axis. I'm going to put the distance on the y-axis. Don't forget to label that y-axis. Remember, we always label the y-axis. X-axis maybe not, but the y-axis we always label. Okay, and then we look and say, well, the times ranged, looks like 29 is our lowest and 94 is the highest, so we need to cover 29 through 94. So I'm just going to go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. I'm going to extend that line out to make sure I cover it. Remember, we need consistent indices anytime we're doing a graph. And then the distances range from, looks like 14 up to 86. So I'm going to number my y-axis to cover that. 10, 20, 30, 40, 50, 60, 70, 80, 90, and extend that so we can see that. So now we have our axes in place, and we're ready to create our scatter plot. Just label it to make sure we know what we're talking. Now, sometimes a scatter plot is referred to as an XY scatter plot because you're looking at the x-axis and the y-axis and these ordered pairs that are being plotted on it. So we tend to sometimes call it the XY scatter plot. But a scatter plot is just what it sounds like. It's a scattering of data points. There is no particular order to them. So all we're going to end up with is a bunch of dots scattered on this plot. And we're just going to start with the first one and work our way through it. So we have 51, 56. So we come over to 51, we go up to 56, and we put a dot. 29, 14, so 29, 14, and we put a dot. 64, 24, 64, 24, and put a dot. 68, 48, 68, 48, and put a dot. 94, 86, 94 up to 86, and put a dot. 33, 25, 33, 25, put a dot. And then 89, 66, 89 up to 66, and we put a dot. So now we see that we have a scatter plot. Let's make sure that all these are good. So we got 51, 56, 29, 14, looks good. 64, 24, looks reasonable. 68, 48, looks good. 94, 86, 86, yep. 33, 25, reasonable. And 89, 66. Okay, yeah, looks reasonable. Just making sure that my numbers are in reasonable spots. You should always check that and see. Okay, so now that I've got that, that is a scatter plot. There's nothing else to it. We don't connect the dots. Remember I said that there's no specific order to it. You just have a bunch of data points that came in and we plot them. Now, what's the advantage of plotting these? Well, now that we've got this scatter plot, we might see some sort of a trend. What I mean by a trend is, as X increases, do we see something specific happening to Y? And in this particular case, I happen to see that it seems to start as X is small, Y tends to be small, and as X gets bigger, Y tends to get bigger. In fact, I'm going to put in blue a guesstimated trend line, basically saying that it does something kind of like that, right? As X increases, Y increases. So I'm calling this a guesstimated trend line. Put in there, that we see this relationship. Some people might call this relationship a correlation. How well the two variables relate to one another. And we see that this is a pretty good relation. As X increases, Y does tend to increase. Is it always that way? Is it exact? No, of course not. We see that here. We've got data values that are way off from that. It dropped down here. It didn't keep going up, right? It went way up here, dropped down, went back up. So it's not exact, but we definitely see that there's a trend. We can expect if someone drives a longer amount of time, that they're going to cover a longer distance. Now, when using these scatter plots and looking at the trends, we do have to realize that we can only guess safely in the range of our data. Meaning I can look at this and say, yeah, someone who drives for 50 minutes is probably going to drive somewhere around 50 miles. But I can't say that someone who drives for 150 minutes is going to drive about 150 miles. And the reason I can't do that is because my data is in this range. I don't know what happens after that. They might be a commercial driver, and the requirement is that every 2 hours they have to stop driving for a half hour. Well, isn't that going to change the distance that they travel in that amount of time? So we don't know what happens beyond that. But being able to draw a scatter plot definitely helps us to look at the data and get a better idea of what's happening. We may not have noticed as much in this blur of numbers that X and Y both tended to increase together. Well, let's talk a little bit about correlation. Now, there are 4 general types of correlation that we're going to discuss at this point. So I'm drawing a scatter plot, right? So we see here that as X increases, Y tends to increase. This is called a positive linear correlation. I'll put it down here. Positive linear correlation, meaning that as X increases, Y increases, and it does so in a linear fashion, meaning I can draw a line that estimates what's happening. Our second one and please make sure you get all the dots in the correct places if you are taking notes on this. The second one is called a negative linear. Negative linear correlation, because as X increases, Y decreases. Now, if you remember graphing when you were younger, when you dealt with graphs, you talked about slopes. A positive slope was one that went up as you went to the right. A negative slope was one that went down as you went to the right. So you can see that positive linear, positive sloped line, negative linear, and negative sloped line. Okay, our third one, as you can see, the trend is very difficult to discern here, if there even is a trend. We call this a weak correlation. Now, some people may say that there's no correlation in this, but we're going to see in the upcoming little videos that saying there's no correlation is a very specific thing. So we're going to call this weak. And then the fourth one the rainbow correlation. No, it's not really the rainbow correlation. This is a nonlinear correlation. A nonlinear correlation, meaning that there's obviously some sort of relationship, some correlation between the X and the Y values. They're trending, but that trend is not a line. It's this curve. So that's a nonlinear correlation. In this course, we're going to deal specifically with discovering linear correlations. If we have a nonlinear correlation, we're going to end up trying to treat it as a linear correlation, which means it won't be as accurate as it could be. You can actually go beyond linear correlations and get into nonlinear correlations and figure out how that works and the best fit curve for it. But we don't have to do that, so that's very nice for us. Makes our life a lot easier. So positive linear, negative linear, weak, where it's just all over the place, or nonlinear. So those are some ones that we would deal with, and we're looking mainly for positive, negative, we're looking for linear. When we talk about correlation, what are we talking about? Well, like I said, it's the relationship between the x and y values. How do they relate to one another? And we actually tend to talk about correlation coefficients. Correlation coefficient, R, is a measure of how well the x and y variables correlate or relate to one another. Okay. So R, and this is dealing with a sample, so it's the Roman letter R. If we were dealing with a population correlation, that would actually be the Greek letter rho, R-H-O, rho, looks a lot like this. Okay, if we were doing with a population, but we're going to deal strictly with the sample correlation coefficient. And the correlation coefficient tells us how well and in what way the x and y variables correlate. Now, R will always be between -1 and +1. It's always between -1 and +1. It will never be larger than +1, and it will never be more negative than -1. You can't have a correlation coefficient of 2. You can't have a correlation coefficient of 1.1. You can have a correlation coefficient of 0.97. Okay, so the correlation coefficient is always between -1 and 1. When R is equal to 1, you have a perfect positive correlation. Perfect positive correlation, which means that if you were to create a scatter plot for the data, you could draw a line through all of the data points. A straight line would go through every single data point. That's a perfect positive correlation. And it would, of course, have a positive slope. It would be going up. When R is equal to -1, you have a perfect negative correlation. So a perfect negative correlation. So again, you could draw a line straight through all the data points, but that line would slope down. When R is equal to 0, you have no correlation. Remember, I said that no correlation was a very specific thing. So when R is equal to 0, exactly 0, there is no correlation. When the absolute value of R, is less than 0.5, then we can say that we have a weak correlation. And when the absolute value of R is greater than 0.5, we can say we have a strong correlation. So what's that mean? Well, remember that 1 is a perfect positive correlation. -1 is a perfect negative correlation. Absolute value of 1 and -1 is 1, right? So if we have an absolute value of R that's 1, you have a perfect correlation be it positive or negative. If r is equal to 0, we have no correlation. So in between there, from 0 to 0.5, we have a weak correlation, meaning it's closer to having no correlation than it is to having a perfect correlation. Between 0.5 and 1, we are closer to a perfect correlation than we are to having no correlation. Now, some people may tell you that it really depends on certain ranges, and they may set you up and say that if r is between 0 and the absolute value of r is between 0 and 0.3, then you have a weak correlation. If r is between 0.7 and 1, then you have a strong correlation, and then you have this no man's land in between that's neither strong nor weak. And it's really personal preference as to how you define these. Whether you want to have that buffer in there and say, yeah, that's no man's land, it's not strong, it's not negative. I find it easiest to just use 0.5, it's halfway between 0 and 1. So we can just say, hey, if the value is between 0 and 0.5, then we've got a weak correlation. If the value is between 0.5 and 1, then we have a strong correlation. So let's look at some possibilities with this. And here's where I'm going to give you something else too. I tend to, in fact, I require 4 decimal places when dealing with correlation coefficients. So anytime you give me a correlation coefficient, it should have 4 decimal places. All throughout my math teaching that I do, I tend to like to see 2 decimal places. Correlation coefficients are where I require 4. So let's say I have r equal to 0.3912. And I want to determine what type of correlation I have. Well, I look at it and I go, okay, it's positive, so I have a positive correlation. And then I look at the number and I go 0.39. Okay, that's closer to 0 than it is to 1. It's less than 0.5. So therefore, I must have a weak positive correlation. You must state both of those things. It's not good enough to just say it's a weak correlation. Weak, fine, but in what direction? It's not enough to say it's a positive correlation. Yeah, it's just positive, but is it a strong one or a weak one? So any values that are not 0, -1, or 1 are going to be defined by weak or strong, positive or negative. It's going to have both parts to it. Obviously, if you have r equal to 0, then you're going to say there's no correlation. If I have r equal to 1, you'll say that's a perfect positive correlation. R equal to -0.7923. R equal to -0.7923. What type of correlation do we have? I see a negative sign, so therefore it's negative, and 0.79 is greater than 0.5, so we have a strong negative correlation. Okay, so a strong negative. Strong because it's greater than 0.5, negative because the sign is negative. It's got a negative slope to it. R is equal to 1.7624. What type of correlation do we have? Okay, we see the sign is positive. We see that it's greater than 0.5. So therefore, we say NA, not applicable. Why not applicable? Correlation coefficients can only be between -1 and +1. This is greater than 1, which means someone made a mistake somewhere. That cannot be a correlation coefficient. Cannot happen. R cannot be equal to 1.7624. Can't happen. Someone made a mistake somewhere. Maybe they did a calculation wrong. Maybe some of the data was wrong. Something happened, and even the data being wrong couldn't do it. It'd have to be somewhere in the calculation, or even just a typo. Maybe it was supposed to be 0.7624 or negative 0.7624, and they just wrote the wrong thing in there. I don't know. But that's what we're looking at for the start of correlation coefficients. How do we interpret them? 1 or negative 1, perfect positive or perfect negative. 0, no correlation. If we're closer to 0 than we are to 1, then we're weak. If we're closer to 1 than we are to 0, then we're strong. You've got to define strong or weak, positive or negative, unless you're having to say directly no correlation or perfect positive or perfect negative. And then make sure that you're not looking at correlation coefficients that are greater than 1 or less than negative 1, because that's impossible. So that's our intro to the correlation coefficient.